Welcome to the opening lecture of the 2015-2016 Core Physics Review. My name is Srinivasan. I'm course director at ABR Physics Review. Just in these past 2 days, hundreds of residents across the country will have seen the opening lecture that you're about to take part in. We have an exciting agenda for you today. This is a very unconventional core physics lecture. So initially, we're going to spend about 10 minutes just talking strategy. So I'm going to ask some multiple choice questions to the audience to get a sense for where you are in terms of thinking about core physics, and also to give you some of my thoughts on test preparation. And then in the second part, which probably will be from minutes 20 to minutes 60, I'm going to use a whiteboard style teaching method to give you everything you need to know about Xray production. The goal here is to filter out all of the unnecessary material and just focus on what's necessary for the exam, and to think about this from a conceptual standpoint so that you can carry this forward into your career. When I do the end of the year review in April, it's going to be in Cambridge, Massachusetts, and in Palo Alto. That is a completely PowerPoint-based 4-day review, and it's filled with interactive multiple choice questions like the ones that you're going to see at the end of the lecture today. The foundational lectures that I have for institutional subscribers, those are all whiteboard style lectures, like the first part where you're going to see me talk about Xray production. Okay, let's get started with some of the strategy related topics. So I have a few multiple choice questions for you to kind of get a sense for where you are as an audience. So use your cell phones or your laptops to log into this website, polev.com/corephysics, and go ahead and select the best answer to this question for you. And I'll give you just a few seconds to finish logging in and voting. Okay, let's take a look at the preliminary results here. And it looks like we have a predominance of PGY2 residents and a few residents from the other years, as well as some others. Good. Okay, so I think everyone should have gotten that answer correct. You've been studying for that answer at least for the whole of this year. Let's look at the answers to this question. So go ahead and log in your best answer. What does your life look like after training? Okay, so let's take a look at what the results are here. So it looks like there's reasonable parity between academic and private practice, a little bit more in favor of private practice, and then a smattering of people that are exploring other career options. The key point here is that when you think about core physics, it's relevant to all of these options. So this year, if you're a third year and you're thinking about how you're going to study, think about also how this material is going to relate to where you're going to be after you finish residency. Learning core physics is not just about passing the core exam, although that's a really, really important part of it. 30% of the exam is physics, and if you fail the physics portion, you have to retake the entire exam, even if you did really well in the clinical portion. So it's worth paying attention even for that reason alone. But if you're going into academic radiology or private practice, you are fundamentally running a business. So really, options A, B, and C are all the same when it comes to thinking about core physics. And the reason is that when you're running a radiology practice, you're going to be making purchasing decisions for equipment. And the last person that you want to consult on for an opinion on the equipment that you're purchasing is the salesperson. You need to be able to buy a new tomosynthesis machine for your private practice group without asking one of the major manufacturers what their opinion is on which model you should purchase. When you have a referring physician that asks you to rule out a head bleed, you need to be able to identify artifacts and redo the scan if necessary based on your understanding of image quality. And safety issues for your patient, the sake of your patients, for the sake of national regulations in your practice, these are all things that you're going to learn in the process of doing really well on core physics. And that's what I'm going to try to communicate to you over the course of this year. Okay, let's see where you are emotionally in thinking about physics for the core exam. As you can see here, there's a full spectrum of emotions when it comes to thinking about physics. And so the point of this question is to tell you, wherever you are on this spectrum, you're not alone, okay? So I was actually on the D and E end of the spectrum at the end of my second year because I had hardly done any studying for the core exam. I spent a lot of my time at work doing the clinical work, and then after work I was either relaxing or doing research related things. Neither of those really relate to doing well on core physics. And over the course of the last 3 years of being involved in teaching core physics, what I've learned is that there's really just a small kernel of information that you actually need to know. And a lot of stuff that you see out there in the review literature is extraneous to what you need to be a good practitioner and what you need to do in order to score really highly on the core. So even if you're over there in D&E, you're still, even if you're taking the November recertification, you're still many weeks away from the exam, and if you're taking it in June, you're almost a year away from the exam. So you're going to be able to achieve this material, and I will empower you to get there. There's a lot more that I want to say about strategy, but I'm going to table that for the online foundational lectures or the end of the year review when it comes to thinking about how you're going to maximize your performance on the exam. What I'd like to do now is transition to the physics portion of the lecture so that we have time to get through that entire section and then get to multiple choice questions at the end of the exam at the end of the lecture to test your cognition. So let's talk about X-ray production, which is the topic for today. What I'd like to do when I start this topic is to talk about the X-ray tube in the broadest sense, okay? So you've all seen an X-ray tube when you've walked through the radiology department. It's really just usually a white plastic box, okay? And out of this box, it's an X-ray tube. So out of this box, what you see is X-rays coming out. And I'm going to draw them as little circles, okay? So X-rays, you learned in high school probably that light can behave like a wave, or it can also behave like a particle. For the sake of this exam, you only need to think about X-rays, which are a type of light. You only need to think about them as particles, okay? So that's what I've drawn here, is little particles or packets. So X-rays are actually packets of energy. Just like M&Ms. M&Ms are little packets of energy, okay? And so I'm going to write here X-ray photons. And that's what sprinkles out of an X-ray tube. X-ray photons are packets of energy, okay? And I'm just going to mark this here. This is the X-ray tube, just for clarity. All right, great. So what else do we know about M&Ms? M&Ms they don't have different flavors, but they certainly have different colors. Okay, and so it turns out that X-ray photons also have different qualities, and the quality that we care about most is just the energy associated with each of these packets. So I'm going to assign an energy to each of these 5 X-ray photons that I've drawn here. So here's one X-ray photon that has an energy of 30 kiloelectron volts. So for this lecture, I'm not going to tell you exactly what a kiloelectron volt is, except to say that it's a unit of energy. Okay, so let's assign a few energy levels for the rest of these photons, okay? So here we go. This photon has an energy of 30 kiloelectron volts. Let's say this one's got 120, and I'll assign 2 more. This one right here has an energy of 60, and this one over here will have an energy of 60, okay? And let's just erase this one here, okay? So we have 5 photons. Each of these have a different energy, okay? X-ray photons. Let's do a little experiment. I'm going to place, since it's November lecture, or we're nearing October, we're almost in Halloween season, so I'm going to put a little cauldron underneath this X-ray tube, and I'm going to collect all of the 5 photons that sprinkled out of this X-ray tube, okay? So there was 30, 30, 60, 60, and 120. And now what I'm going to do is I'm going to actually plot the distribution of X-ray photons that came out of this X-ray tube. Okay, so let's draw a plot. The reason why I'm introducing this plot to you is not because it's some sort of 16th century method for torturing radiology residents, but because this is a sort of testable concept for the exam. And so just to let you know, the name of this plot that I'm going to be explaining is called an energy spectrum. Okay, so how does this plot work? So it's going to tell me what the distribution of X-ray photons were in this cauldron coming out of the X-ray tube. So on the x-axis, I have units of energy. And remember, those are called kilo-electron volts. Okay, just jargon for now, but just think of it as a unit of energy. And on the y-axis, I'm going to put percent of total photons, percent of all the photons in the cauldron. Okay, so let's get started with filling out this plot. So at 30 kilo-electron volts, I'm just going to put 2 X marks because I had 2 photons at 30 kilo-electron volts, okay? And then I'm going to go over to 60 and put 2 more X marks because I had 2 more photons at 60, I know that. And then 1 photon at 120 all the way up here, 120 kilo-electron volts, the highest energy photon in the cauldron. So how am I going to get percentage of photons? Well, I have 5 photons in the cauldron, or 5 photons that I collect out of the X-ray tube. And so 2 out of 5 is 40%. So I'm just going to mark 40% on the y-axis and put a little data point here. So what I'm getting from this is that 40% of the photons that came out of this X-ray tube had an energy of exactly 30 kilo-electron volts. And similarly, I had two X-rays at 60 kilo-electron volts and just 1 X-ray photon at 120. So that's 1 out of 5, which is 20%. So the data point's lower for the 120 kilo-electron volt energy level. So in between, I didn't have any photons that I collected at these intermediate energies. So the value of this graph is 0 in between. 0% of the photons had any of these other energies. Like, for example, there are no photons. I can see from this graph that there are no photons that have an energy above 120. So being able to interpret this graph in that way is really important. You need to be able to look at this and say, okay, this X-ray tube with the settings that it's on right now is not producing photons that have an energy greater than 120. Okay, so this is what the energy spectrum is going to look like. It's going to have these peaks wherever we do see photons at that energy, and the higher the peak, the more photons there are at that energy. So it turns out that real X-ray tubes, like the ones that you see in your department that are being applied to patients, don't have an energy spectrum that look like this. Instead, I'll draw for you what the real energy spectrum might look like in blue. So there's a broad component, photons that have a wide range of energies. And then there's a narrow component that rides on top of this for a bunch of photons that have a very narrow range of energies. Okay, and so what we're going to do is figure out, we're going to take a step back and just ask how are X-ray photons sprinkling out of this X-ray tube, the big picture, and then we're going to come back and explain this energy distribution, the fact that there are 2 distributions of photons coming out. Okay. So let's put this energy spectrum to the side for now, and let's come back to the X-ray tube and just get the big picture on what's going on. So here's the X-ray tube. So to start, we talked about the X-ray tube as just this giant piece of rectangular plastic or tube-shaped plastic that was sprinkling out these X-ray photons. So let's just draw that big piece of plastic. Okay, great. So what's going on the inside of this is that on one side we have metal, a piece of metal, and the piece of metal has a name. It's jargon, but you're going to need to be able to identify this for the exam, and this metal is called the anode target. Okay, great. On the other side of this X-ray tube, we have an electron. So I'm just going to draw this. This is an electron that we produced. I'm not going to tell you how we produce this, but we're able to generate electrons on one side of this X-ray tube. And then we're actually able to accelerate this electron we're able to apply a force and accelerate this electron into the metal target. It causes some sort of a collision. And then, so basically what's happening is by accelerating this electron, we're giving this electron a bunch of kinetic energy. Okay, energy. We're giving this electron energy because kinetic energy is related to the mass of the electron, and it's related to the fact that we can move this electron. So by accelerating, we're giving it a bunch of energy, and then after the collision, out comes an X-ray photon, which is a little packet of energy. X-ray photon. So this is more energy. This is a little packet of energy, right? So no big surprise. Energy in, energy out. Conservation of energy, okay? So most of the energy, actually, it turns out, doesn't go into this X-ray photon. It actually goes into heat, okay? So like 99% of the kinetic energy is going into heat, and just 1% is going into producing an X-ray photon. It's kind of the same thing with a light bulb on the wall, right? You're putting in energy by plugging it into the socket, and some light comes out, but a lot of what's coming out is heat. Same kind of concept of inefficiencies, okay? So heat, okay? Second order detail is that in order to dissipate this heat, you actually need to bathe the X-ray tube in oil. And another second order detail, you actually have to rotate this anode target, which is this piece of metal, so that the X-ray beam, so that the electron beam, wherever it's hitting the metal, doesn't actually end up melting the metal because of all that heat, okay? So the only other information, like detail I want to give you in this high-level view, so I'm just going to emphasize conservation of energy. That was a big concept here. So the only other concept that I want to make sure you have about X-ray tubes in this high-level view is that in order to accelerate this electron, how are we doing that? Let's say we want to accelerate it faster to get even more kinetic energy so that we can get even higher energy X-ray photons out. How are we going to do that? And so we have a little knob here that we can actually quite literally adjust. And your X-ray technologist does this all the time. You even do it without knowing it. Let's say when you're doing a barium enema, whenever you change settings on the machines that you use, it's actually changing this particular dial. And this is the voltage that you apply across the X-ray tube. And so the way this works is that when you apply a voltage across the X-ray tube, it kind of acts like this little metal plate has a negative charge and this plate has a positive charge. And you probably learned from electrostatics back in high school that negative charges repel, positive charges attract, right? Opposites attract. So I said that slightly incorrectly. Let me just say it again. A negative charge and another negative charge are going to repel, and a negative charge and a positive charge are going to attract each other. So by applying this voltage, we're causing this plate to repel the electron, cause it to accelerate into that metal, and also it's also being attracted on the other side by this positive charge. Okay. All right, good. So does anyone know the name for this this tube voltage? Normally I would ask you in person. For now, I'll just tell you the answer, or you can shout it out in class to show off to your classmates. So this voltage is called the tube voltage. This is a piece of jargon that you do need to know, okay? Your technologists know this information, and you're going to want to know it as well. Good, so that's what we have. The X-ray tube is all about conservation of energy. You can crank up the tube voltage to increase the energy of the X-ray photons coming out, and the reason for that is because you're able to accelerate these electrons faster so that when they smash into this metal target, they have more energy left over to produce these X-ray photons. Great. So right now, I've just told you one process to explain X-ray production, but we have more work ahead of us because we probably have two processes going on. One process in this collision that's causing this broad distribution of X-rays, and another process in this collision that's causing this very narrow distribution. So right now I'm going to give you the names for those two types of processes, which are also the names of the photons, X-ray photons, that are produced by each of those processes. So the first process is called breaking radiation. And the second process is called characteristic radiation. So now what we're going to do is talk about breaking radiation, because it's actually it's the easier of the two to think about. Okay, so let's talk about breaking radiation. All right, so in order to explain breaking radiation, I'm going to draw the X-ray tube for you again. Remember this large plastic box. Okay, nothing's changed about this box. I still have a little electron on this side here that I've generated, that I'm getting ready to accelerate into the metal target. This time, I'm going to draw the metal target in a little bit more detail. So I'm just going to put the metal target here as this box. I'll remind you this is called the anode target. So I'm just going to put anode target here. And just like any other piece of matter, like the desk that you're using or the chair that you're sitting on, an anode target or a piece of metal is made out of atoms. Okay, so I'm going to remind you, what is the structure of an atom? This is kind of where I started at the end of second year. It's not that you don't know this information, it's just that you've been spending a lot of time learning a tremendous amount of valuable clinical information, and you may not have had time to discuss or refresh your memory on some very basic things that are going to come back to you very quickly and easily. So let's just remind ourselves, what is an atom made out of? So at the center of an atom, you have protons and neutrons. Okay? So protons are little positively charged particles, and neutrons don't really have any charge. So you have a bunch of protons and neutrons. You don't necessarily have to have the same number of protons and neutrons inside a nucleus. But because the protons are positively charged, the neutrons don't have any charge, the nucleus overall is positively charged. Okay? Now, if you think of this like an analogy to our solar system, the nucleus is kind of like the sun. It's at the center, and then you have different orbits. You have electrons orbiting the nucleus at different distances. So the innermost shell of orbits that are occupied by electrons, these are my little electrons here, is called the K shell. Okay, this is jargon that you do need to know. Okay, so I'm going to write K shell here. Great. Now, there are a bunch of shells, just like there are different planets orbiting at different distances to the sun. There are a bunch of additional electron shells, okay, or orbitals. But the one that you care about the most, in addition to the K shell, is just another one of these outer shells, shells that are farther away from the nucleus than the K shell. So I'm just going to generically call that one that I've just drawn an outer shell. Okay, great. So basically you have a metal that's packed full of atoms, and this is just one of those atoms that I've drawn inside your anode target. So we were talking about breaking radiation. What's going on with breaking radiation? So we know that somehow we're able to accelerate an electron, give it a whole bunch of kinetic energy, and then out comes an X-ray photon, which is a packet of energy. Okay, so what's happening here is that this electron's trajectory, instead of just going straight through the metal, it's actually curving on its way through the metal. Okay, and by curving, it's curving because it's interacting. This is a negatively charged electron. It's interacting with that positively charged nucleus and some of the native electrons. So by curving, what's happening is that it's losing kinetic energy. So I'm going to make a smaller letter kinetic energy. Let's just exaggerate this. So you start out with a whole bunch of kinetic energy. You end up with very little. And so we have conservation of energy. That energy just can't go, disappear into thin air. So that energy actually gets released as an X-ray photon, which is a packet of energy, right? So you can kind of see that if this trajectory gets disrupted a whole lot, I'm going to lose a lot more kinetic energy. I'm going to release a higher energy X-ray photon. But if my electron just happens by chance to make it through without really changing its trajectory at all, then it really hasn't lost much kinetic energy, so it doesn't have very much to give up to X-ray production. Okay, and that's why. So let's just show here. So this is this trajectory is going to produce the higher energy photons, and this is because that trajectory is losing a lot of kinetic energy for this electron, and so that's going to result in the photons that you see all the way out here at 120 kiloelectron volts, really high energy photons, X-ray photons. On the other hand, the lower energy photons are going to come from this trajectory here, where the electron really didn't change its trajectory. And these are these electrons down here. And so you get this full distribution, okay? You get low energy photons, you get high energy photons, and then you even get intermediate energy photons. Okay, so what we've shown is that breaking radiation produces this full range of energies. And the reason is because the electron that's being accelerated into this metal target can take a variety of trajectories. As it's breaking, just like a car brakes, in the process of releasing the X-ray photon as the excess energy. Okay? All right, so hopefully that's clear. Let's talk about characteristic radiation now. How are we going to get this very narrow range of energies that of photon energies? Certainly not from breaking radiation, we've seen that, and so there must be something else going on here. So let me explain that. So let's go to that. Characteristic radiation. All right, so let's start again. We have the X-ray tube. It's a large piece of a box of plastic, okay? We have our electron on one end that we've generated in order to accelerate it. We gave it kinetic energy by cranking up the tube voltage, okay? Don't forget the tube voltage. And then let's just draw this anode target again. So we have the positively charged nucleus. We have the K shell electrons. Here's one here. Here's another one. Just going to remind you, K shell. Then we have a bunch of other shells, and then we have the outer shell electrons. Okay, this is just, outer shell doesn't necessarily mean the outermost shell. It can mean a shell that's just more outer than the K shell, which is the innermost shell, okay? But just think of this as an outer shell electron. Outer shell, this is the outer shell, okay. All right, so here are a whole bunch of electrons in the outer shell. Now we've accelerated this. This is our electron that we generated. It has nothing to do with the electrons in the metal target, okay? We're generating this electron off to the side here. We're accelerating it towards the anode target. And what's happening this time is this electron comes in and it knocks out the K shell, one of the K shell electrons, okay? So that goes flying. And I'm going to sort of draw the vacancy here in blue. You now have a vacancy, okay? You have an empty spot in the K shell that an outer shell electron can occupy. So let's watch that happen. So this outer shell electron is going to make its way down. It's going to kind of drop in to the K shell vacancy, okay? So that's what I'm drawing here. Now what's happening in this process is that you're taking an outer shell electron which has a higher energy state and putting it into a lower energy state. Well, we know again from conservation of energy that this is going to, that energy difference doesn't just disappear into thin air. That needs to go somewhere, and where that goes is characteristic radiation, a little packet of X-ray photon energy. But the energy of this X-ray photon is exactly the difference between the outer shell energy and the K shell energy. It's this difference that's the precise energy of this X-ray photon. It's a characteristic of the metal because the distance between the K shell and the outer shell relates to the atomic structure, which, every element has a different atomic structure. So if I choose a different metal target, I'm going to get a different energy difference between my outer shell and my K shell. So just by looking at this energy that's coming out of this process, I can actually tell what metal is being used because the energy of this photon is characteristic of that metal. And that's why we call this characteristic radiation. It's a characteristic energy or a signature or hallmark or fingerprint energy for this particular metal type. Okay, so that's great. For the purpose of the exam, you're going to want to go into this exam having memorized the characteristic radiation for a select group of anode targets, a select group of metals, okay? And so the thing is that memorizing the characteristic radiation is actually hard to do because the specific energies that you have to memorize are numbers like 20.7, I'm just making up these numbers, or 18.6, numbers that have a decimal point at the very end. And it's just hard for me. I don't generally like memorizing things. So what I did in preparation for the core exam a few years ago is I went in having memorized a minimal set of information. And that's actually the minimal set that I've included in Radiology Simplified. The physics portion is essentially the minimal set of knowledge that I wanted to go in having memorized in order to do well on the exam. And so let me show you how you can memorize the characteristic radiations, or at least get them all correct if they happen to ask this to you on the exam, without having to memorize those weird numbers. Okay? And so to help you memorize that, I need to introduce one more physics concept, and that's the only reason I'm introducing this concept. So this is called the K-shell binding energy. Okay, so I'm going to explain K-shell binding energy. So think about that metal target again, okay? You have the nucleus that's positively charged, you have the K-shell, and here's your K-shell electron, and then you have some sort of an outer shell, and many other shells, of course, but here's the outer shell, or one of the outer shells, and you have another, you have electrons circulating in the outer shell. Okay, so what is K-shell binding energy? K-shell binding energy is the energy that it takes to take this electron in the K-shell and move it all the way out to infinity, an infinite distance away from this anode target. Okay, it's kind of like, it's very similar in analogy to taking a space shuttle at the surface of the Earth, and how much energy does it take to take that space shuttle from the surface of the Earth and bring it all the way out to infinity, right? Gravity is pulling that space shuttle in. The farther out you go, the less pull the gravity has, but all along the way you have to use energy in order to get that space shuttle away from the surface of the Earth. And so the K-shell binding energy is identically the amount of energy it would take to pull an electron away from the K-shell all the way out to infinity. So this is the K-shell binding energy, okay? So how does that relate to the characteristic energy, which is the the quantity that you may be asked about with regards to X-ray production? So the characteristic energy is the energy difference between the K-shell and the outer shell, right? So one thing you can see is that clearly, so I'm going to label that characteristic energy, okay? Characteristic energy. So immediately, you should be able to see that the K-shell binding energy is way bigger than not way bigger, it's definitely bigger than the characteristic energy. But it turns out that once you get to this point with your electron, going from here all the way out to infinity, it actually doesn't require that much energy because the electrostatic attraction between the electron and the proton is diminishing rapidly as you move away from that center. And so this energy, even though it looks like a large distance on my diagram, it's actually very little. So it turns out that the characteristic energy is just a little bit less than the K-shell binding energy. It's just a little bit less than, I don't know if there's a symbol for a little bit less. There is a symbol for a whole lot less, but I don't know if there's a symbol for a little bit less. So it's a little bit less than the K-shell binding energy. Okay, cool. So we have like the K-shell binding energy concept, okay? Just like a space shuttle going from the surface of the Earth out to infinity. Now let me just write down the K-shell binding energies that I want you to have memorized, okay? So these are the metals that you're going to need to know the K-shell binding energy for. Molybdenum, rhodium, silver, tungsten, iodine, and barium. So here are your K-shell binding energies. And they're in units of kilo-electron volts, the same units of energy that we've been using up till now, okay? So I'm just going to move this molybdenum down here so it's not confusing to you. All right. Molybdenum, rhodium, and this is all in the book, by the way. So, all the diagrams here, and all this information, the essential information, is in Radiology Simplified. So, okay, let's just write down the energies here. So molybdenum, 20, 23, 25, 70, 33, and 37. So throughout the year, as I was leading up to taking the core exam, I just wrote these numbers down, kind of like memorizing a telephone number. And I would quiz my friends in the hallway, like, hey, do you remember the K-shell binding energy of silver? Oh yeah, 20, 23, 25. Yeah, it's 25. Silver is 25. And on the exam, they will provide you a piece of paper for you to write your notes on. And so there's no reason why in the first couple of minutes of this exam that you shouldn't just dump all of your memory onto that exam, onto that paper, in order to refer to it later on in the exam. So how does this work in terms of answering questions? Well, if someone asks you what the characteristic energy is of silver, then you're not going to answer 25 because you know that the answer is slightly less than 25. Remember, the characteristic energy is slightly less than the K-shell binding energy. That's this thing right here. So typically with multiple choice questions on exams in general, people are not trying to absolutely destroy you. And so you're not going to have like 5 options that are less than 25. I mean, it's extremely unlikely that you'll have 5 options less than 25 for the characteristic energy of silver. And so you're automatically, without having memorized this minutia about the characteristic energy of silver, you're going to be able to throw out a bunch of options. Like if there's an option that's 25.1, that cannot be the characteristic energy of silver, because characteristic energy is going to be less than the K-shell binding energy. And just as an added bonus, there's something else that I talk about in a subsequent lecture in my online archives and also review at the end of the year, which is a concept called K-edge. It's unrelated to this lecture. It's not about X-ray production, but the K-edge, it turns out, is a number you're going to have to memorize. But if you have the K-shell binding energy, you don't have any more memorization to do, because you can get that off of the K-shell binding energy. So prepping for this exam is all about getting the stuff that you need to memorize into a really compact form so that you don't have to like spend your time memorizing. I think that, I mean, we have the internet today, we have Google, we have all sorts of tools to store memorization related information. And this is part of the reason why this exam was reformed, is to kind of get away from having to memorize recalls and go to the conceptual realm where you're actually using your capabilities. So that's what I want. At this point, you've covered everything you need to know about X-ray production. Let's put this to test, and I'm actually going to ask you a few questions to kind of stretch your mind and get you oriented toward how all this converts to questions on the exam. So let's see, you can get your voting method, which can be your cell phone or your laptop. You can get that ready by going to polev.com/core physics. And here's your first question. What is the K-shell binding energy of tungsten in kiloelectron volts? Okay, give yourself a couple more seconds to lock in your answer. All right, let's see where you are here. So, nice job. There's a predominance of response for D, which is the correct answer, 70. This is a recall question, okay? You either know the answer or you don't. When I teach my students about strategy for exam day and exam day psychology, one of the things I talk about are the 3 types of questions. The first type is a recall question. The second type is a reasoning question, something that you might need to know a little bit of memorization for, but then you have to do some mild reasoning in order to ultimately get the answer. And the third type of question is called an FU question. This is just a term that I've made up. And the reason why I call it an FU question is because it's a question that really shouldn't have been asked of you in the first place. This is just generically something that exists on every multiple choice exam. Over the course of this year, by whittling down to that kernel of information that you need to know, you're going to be able to appreciate the distribution of knowledge that that's expected of you going into this exam. And so when you get an FU question, you'll see this is clearly an outlier. Maybe it's a memorization question that's just such minutia that you couldn't have possibly been expected to have memorized to that level of detail. It wouldn't have been practical. And so the key point is to recognize FU questions when you see them, be able to reset and move on emotionally so that you're not, making mistakes on the next 5 questions just because you were tripped up psychologically on the FU question. So there's a lot more about game day psychology in the foundational lectures for institutional subscribers, and also at the end of the year review if you come to that. All right, let's go to the second question. Which type of X-ray is most critical? And I'm going to reset the poll, so go ahead and relog your answers here. Which type of X-ray is most critical for imaging in most present-day mammography? Okay, let's take a look at the answers here. This is a kind of a combination of recall and reasoning because you're not going to be able to memorize answers to questions like this for every possible question that's asked on the exam. So you need to use a little bit of reasoning. And you will build this intuition. I have really nice lectures on mammography coming up for the rest of the year and at the end of the year review. So these are kinds of questions you'll be able to attack and take into your practice group. When your practice group, as the youngest member of your practice group, you're going to be the tech-savvy person. And when your practice group needs to make a purchasing decision on that mammography unit, you're going to understand what your options are without having to consult with the salesperson. And so excellent job. You guys, most of you got characteristic. For the people that answered photoelectric C or Compton D, these are not methods for X-ray production. Today we talked about 2 methods for X-ray production, characteristic radiation and braking radiation. And if you're paying attention, you'll see that there's a typo here. Braking should be spelled like a car brakes, not like I've spelled here. It turns out, for those of you who answered braking radiation, you're anticipating the future. A lot of the newest units that are being sold actually are tungsten targets with silver filters. You'll learn about what that means in a subsequent lecture, but they're actually predominantly using braking radiation instead of characteristic. But this is a test-taking skill. If you get hung up on details like that, then you're going to miss what the test taker wants you to select. And what they want you to select here is characteristic radiation. Okay, let's go to the third question. This is a tricky one. The photon energy spectrum changed, so your X-ray tube was producing this green energy spectrum, and then the technologist came by and did something to the machine to produce the red energy spectrum. What did they do? That's basically what it's asking. What single parameter adjustment would guarantee this change from green to red, whether or not a phototimer was used? Okay, let's take a look at the responses. There's always spread for this question, so don't feel bad if you got the answer incorrect. There's a preponderance of support for tube current D. A few people that answered E. I don't see an E option on this diagram here. Maybe that was just a misfire. So let's talk about what's going on here. So when I teach the energy spectrum to my students, I teach them about specific points on this graph that you have to pay attention to. For this, and you don't have to pay attention to every single point on this graph, right? So for this graph and this question, the point that you have to pay attention to is the x-intercept. And I alluded to that earlier in this lecture. So where this green line hits the x-axis, you know that there are no photons being produced at energies greater than this point right here. And then the technologist came by and did something so that the X-ray tube was somehow producing these higher energy photons. That's why this red curve is non-zero all the way out to here on the x-axis. Okay? How do you produce higher energy photons? This is where you've got to use that intuition you built from earlier in the lecture. That dial that the dial that you turn to increase energy is the tube voltage, right? It turns out that the tube voltage, and I didn't tell you this in the lecture, it turns out that the tube voltage has the units of volts or kilovolts, which is 1,000 volts, and the peak voltage that it achieves, that tube voltage actually has a tiny little ripple. And so there's something called the peak tube voltage, or the KVP, just like the maximum possible voltage that the tube could be generating. That determines the maximum possible photon energy that you can produce. And so in order to get higher energy photons, you have to increase the KVP. There's other stuff going on with this graph, like why are you producing more photons overall? That stuff is sort of important detail, but something that I'm not going to be able to cover just in this opening lecture. It turns out that B, C, and D are all kind of very similar answers. And then the other point is that the phototimer, whether it's used or not, is a distractor in this question. Okay, let's go to the last question. What happens to average photon energy if you increase KVP by 2x? That's the peak tube voltage. Okay, let's see where this is. It looks like there is, again, some spread here. There is significant support for the correct answer. Nice job on that. The average photon energy increases by 2. So this is a pretty classic split. There's often a split between A and E on this question. The reason why, so we know that B, C, and D are not correct. This is an important point. So the average photon energy is kind of like the average score on an exam in a class. If you increase the number of people in the class that are scoring really well, then the class average goes up. And so by increasing the KVP, you're increasing the total number of photons that have very high energies. And so the average photon energy is also going to go up. So certainly the average photon energy cannot be unchanged. It can't even go down for sure. So nice job for all of you on avoiding C and D. But it's not that it's unchanged. It turns out that the average photon energy actually does increase. Why is it that it's not going up by a highly variable amount? It's because when you take averages of large numbers, you don't get very much variation. That's why when you do a large clinical trial, you want to average a whole bunch of patients, because you want the conclusion that you draw from that average to not change the next time someone reruns that experiment with that same number of patients, right? So here we're talking about the average photon energy. This is typically collecting across millions of photons, okay? I only had the energy to draw. I could only draw 5 photons for you today without my hand cramping up. But when you talk about average photon energy, we're talking about the average of millions, and that's why it's not really a variable amount. One formula that's helpful to memorize going into the exam is that the average photon energy is about half the KVP value, okay? Now, this is really only true for conventional radiography, and the main reason is because in mammography, you have predominantly characteristic radiation that you're using. It kind of messes up the average calculation, okay? Because you don't have equal representation across all of the energies. You have this massive peak from characteristic radiation, which is the radiation that you use predominantly in current day mammography units. Again, stuff that I didn't cover today, but that's described in the mammography lectures online and at the end of the year review. Great job, guys. I'm going to take the last 5 minutes to tell you about the course offering for this year. So basically what I have is a 4-day review at the end of the year, and it's going to be both on the East Coast at MIT in Cambridge, Massachusetts, and also on the West Coast in Palo Alto. Just in April, 2 dates in April, 4-day review. The format, so in addition to this, the registration fee for the 4-day review also includes Radiology Simplified, which it has both clinical cases, 120 clinical cases, kind of a bonus. We add cases for free throughout the year. But it also has the full physics coverage. That's the minimal set that you need for the exam. It's very image oriented because I'm a very visual learner. So half of the time that I spent writing this book was on making diagrams and working with a professional illustrator to actually include those. And this is all specific to the core exam. And then the 4-day review is really focused for the new exam because it has it's a heavy emphasis on multiple choice questions. So kind of these interactive multiple choice questions that you saw today, the 4-day review is going to be packed with those multiple choice questions. And by the time you get to the April review, that's what you're going to want. You're not going to want hours of just plain PowerPoint didactics. It's going to put you to sleep and wish that you were out there kind of answering more questions from a question bank. So we're going to have a healthy component of multiple choice questions to really get you focused on the material that you need for exam day. I'm also going to be including a heavy emphasis on artifacts, and you can see that online at abrphysicsreview.com. I have the actual curriculum for that 4 days. We're going to cover all of the artifacts that you need to know for this exam, and a lot of it in multiple choice format. Also included in the registration for the 4-day review is whole year support on question and answer. So you as an individual can ask me a question through email, or you can call me, and I will get you a customized answer to your question. So at the top here, this is an example of a question that one of my students asked at the end, just a day before the core exam. Could you explain the difference between attenuation correction in PET and SPECT? So this is the kind of question that you can answer this question with Google, but the issue is filtering out the stuff that's excess information from the stuff that's absolutely necessary for the exam. And that's kind of what I'm able to do with Q&A. It's all about saving you time so you can spend that time either with your family, relaxing, exercising, which is really important leading up to the exam, or with studying your clinical material, which is a sizable portion of the exam. The Q&A forum, by the way, is all searchable. So one thing that my students did last year is they just clicked through questions that other people were asking. The fact of the matter is we're all studying the same information. We're all going to have very similar questions moving forward through this process. And so it's just helpful to have a searchable Q&A forum. And then for institutional subscribers, basically if all of your R3s subscribe through the institution, you'll have access to the 30 hours of lecture that I gave last year to my students that they used in order to score highly on the exam. These are all whiteboard style lectures, just like what you saw today. Different, very different from the end of the year, all PowerPoint, multiple choice interactive review experience, but still extremely useful. My students use this, they can play it back in 1.5x or 2x. It's hosted on YouTube, so you have all those same aesthetics at 1080p. And they basically can go through this at 1.5x speed and be able to do their RSNA modules a lot more efficiently. RSNA modules are fantastic, but there's also stuff that's completely extraneous to the exam and stuff that's very relevant. And so it helps to be able to preview these in order to accelerate through the RSNA modules. Also included in the institutional subscription are 200 multiple choice questions that I'm going to release over the course of the year starting in late October. So 20 questions per section. I break this up into 10 sections of physics. And you can use that to essentially pace yourself for studying and also assess your skills in terms of how they translate from the whiteboard lectures into scoring points on the exam. The results were good last year. We had over 25 residents. They scored between 500 and over 700 on the exam. For the physics portion, the pass threshold, to give you a comparison, is 350. And then there are detailed reviews from 3 of my residents last year across the country, online at abrphysicsreview.com. These are just quick quotations from them, but they have full detailed reviews that talk to you about how they thought about studying for this exam and how core physics review fit into their study process. So your assignment, if you're an R3, or an R1 or R2, everyone should just join Core Physics Coach. Last year, I provided these short video snippets that cover the full range of introductory topics all through mammography, and you can still get those online. Core Physics Coach videos, just Google Core Physics Coach. It's hosted on Vimeo. But this year, starting in late October, I'm going to be releasing about 1 email per month just to keep you on track to say, okay, this is a month that I want you to focus on X-ray production. These are the kind of topics that you need to be paying attention to. This is completely free. The goal is to not spam your inbox, but to give you just a little bit of guidance as you go throughout the year. Everyone should be signing up for this. If you're an R3, I'd like you to reserve your seat as early as possible if you're going to be doing the core review, because the benefit to you is year-round. You're going to be able to start asking questions through Q&A right away. You'll have your copy of Radiology Simplified within a week of signing up for this, even though the review is all the way in April. And also there are just a finite number of seats, so if you want to guarantee, we already have occupied, probably we have about 20 more seats left in the Palo Alto location. So if you want to just have your seat reserved, just do that right away. And then finally, I want all of you to go ahead and review Xray Production in whatever the textbook is that you use. With Radiology Simplified, you're going to see the minimal set, and you're going to see a lot of the diagrams that I covered today, a lot of the concepts And then go ahead and ask me questions if you've enrolled through Q&A forum about today's lecture. And if you're an institutional subscriber, you're actually going to be able to see the intro lecture I gave last year, which was much more extensive, to my students online, and you can ask more detailed questions as well. The website is abrphysicsreview.com. You can reach me in a variety of ways. I'm on Twitter at Core Physics and Facebook, as well as all these other ways to reach me. Thank you so much for coming out today, and hopefully I'll see you all in April or even sooner.